And now that you've seen some of the results of our protocol in action, we also thought it would be instructive to run through an example where our protocol doesn't try to cheat. It doesn't do what we intended it to do and actually demonstrates that it will not send if it deems that it is unable to send. For this case, we developed the L-shaped topology. As you can see on the graphic, the node 1 and node 2 pair on the left, node 1 being the receiver, node 2 being the sender, is the same as previous topologies. But now we have flipped things. So node 3, which is still the sender, has been moved in the vertical direction up, and node 4 has been brought in from the far right closer to node 2, which is the sender. So now what we have is we have both node 3 and node 4 within range of sender node 2. So as this protocol develops, what you'll see is that 3 and 4 will be in communication with each other, and 2 will be interested in sending. And the question is, how will 2 behave, right? What is the exact decision that will be made by node 2 in terms of whether it determines it could transmit or not? And we will now demonstrate how this shows our protocol correctness. As you can see from the two graphics on this slide, this is the results of our L-shaped protocol. At the top, you have the modified graphic, and at the bottom, you have the unmodified protocol graphic. As you can see from both of these graphics, they look to be exactly the same. And they are exactly the same because our modified protocol defaults to the original protocol.
So finally, this brings us to our diamond topology, where we add a y-coordinate in the exposed node instances. So we did add a y-coordinate previously with the L-shaped topology, but now we want to see how our protocol scales with the number of instances of the exposed node problem. So if you look at this topology, you now have a four-way exposed node instance where any given sender can perceive multiple other senders, and the receivers are only able to perceive their one sender. And this was kind of an expansion of our original inception of our experiment. We wanted to vary the distances between these nodes, which we've seen before, but increase the scale at which these instances are occurring. Additionally, we wanted to vary the sending rates and see how our protocol performed when we aren't necessarily trying to maximize the throughput in our network. Starting off simply, this is a demonstration of the average throughput achieved for our modified protocol compared to the original protocol. You can see that the average throughput is getting plotted against the distance between central senders. And so in this experiment, we kept the two top and bottom central senders constant and then varied the distance of the left and rightmost senders in relation to those top and bottom senders. And you can see that we essentially matched the original protocol performance and slightly performed in some sense. But overall, this topology is the most difficult for our protocol to perform well in. I think it's important to point out that, as exposed node instances increase, the hidden node instances also increase, and so it becomes increasingly difficult for us to receive those ACKs at the data link layer that we talked about previously. And so overall, these are promising results for our protocol modification. If we can match the original protocol in this instance, which is the most difficult for us, then we are essentially lower bounding our performance in terms of what was previously available. And so now looking at some more specific results, you can see on the left our individual node performances in terms of throughput achieved versus distance between central senders. And on the right, you can see the original performance. And once again, the key takeaway is in terms of fairness. And you can see that generally speaking, we are a little less fair than the original protocol. If you look at this, distance of 450 to 470, you can see that our nodes on the left in the modified graph are further apart than the nodes in the original graph. This is typically indicative of the fact that different nodes are achieving varied levels of throughput. But on average, we are achieving the same overall throughput in the network as was previously available. And once again, if you think of those thresholds previously defined where we exceed that original performance, you can kind of start to formulate, certain areas where our protocol might actually be preferable to the original. Now we want to look at how our modified protocol performs compared to the original protocol in terms of varied sending rates. Once again, you can see that we pretty much match the original protocol in terms of observed throughput, at least on average. You can see that as the offered throughput increases, we achieve a smaller percentage of that offered throughput. And this, once again boils down to the fact that we are unable to perceive the acknowledgments coming from our receivers.
This brings us to our final graphic, which is a node-by-node comparison of the modified flow analysis on the left and the original flow analysis on the right. The key takeaways from this graph, because it reuses a lot of the information that has just been explained on the previous graphs, is that the overall trend, right, the average of these four lines for both the modified and the original is highly comparable. They trend to almost the exact same pattern, which demonstrates that average throughput in both scenarios is going to be about the same, definitely comparable. Now, the greater distance between these lines is really what we want to talk about on this slide. That greater distance for the modified flow analysis versus the original flow analysis is what we have been using as an indicator of fairness. It's where, like, the left versus the right or the top versus the bottom flow will get a higher proportion of the average throughput than its counterpart. And this is exactly what we want to highlight here. It's a trend that we've shown in some of our previous results and something that continued even into the diamond topology. And that completes our research and the experiments that we ran in NS3. That was the last 2 bullet points, and now I can get back to the main theme: understanding how spatial information can be used to mitigate the exposed node problem. We'll jump into this primary research question in a second, but before I get there, I want to mention the graphic on the slide. The mountain represents all of the challenges that we had to overcome this semester, and we are dressed as that individual on the slide in a suit and briefcase, unprepared to climb that mountain. And so here we are at the project conclusions. We've reached the first summit, we've changed clothes, better prepared to handle the challenges in front of us, and we've learned a lot along the way. Our initial intuition was validated that spatial information could be used in some cases to mitigate the exposed node problem, but of course it was more complicated than anticipated. You had the issue of senders becoming a pseudo-hidden node, and you had additional problems with network topology complexity. And finally, we enhanced our understanding in a number of different areas by overcoming these challenges. We greatly increased our understanding of the basics of wireless networks, maybe even a little more than the basics, our understanding of IEEE 802.11 wireless local area network standards and how they function, and finally, of course, C++ and NS3, which we'll be able to use in any future systems research directions that we may see for ourselves. And this brings us to our future research, represented by the larger mountain in the background. We see this taking 3 possible directions. First, running experiments on an emulator or physical hardware. This would eliminate some of the abstractions assumed by our simulator experiments. Additionally, you could fine-tune the parameters/limitations of our modifications. You could make it such that there were no network instances where we underperformed. And finally, we could test it with variable sending power, either at the senders or the receivers, or on different network standards. We're interested how some of the basic assumptions of well-established networks like static cellular networks would play into the behavior of our protocol. Thank you.